Hello, everybody. We are at the end of chapter 5. This is a lesson or video on section 5.7. 5.7 is about the Jacobian. And instead of the U substitution method you learned back in Calculus 1, which, by the way, you use extensively and very often, now we talk about the UV substitution, okay? So because we have two variables, as you know. All right, so let's look at the last section of chapter 5 on the Jacobian and UV substitution. All right, so Jacobian is the topic, and throughout this, you may be confused about this this idea of transformation and the inverse transformation. Don't worry too much about it, okay? And I'll do my best to try to explain this as clearly as possible. But if you find it a little confusing, I think maybe you should not worry too much if you don't understand all the details, because this is kind of complicated and it's slightly confusing. All right, so it's just a little warning. I want to talk about U substitution first. So a very simple example here is something like this. Let's say you're to find the integral between 0 and 1 of e to the 3x dx, right? And you can quickly recognize, well, you can probably do this without doing directly applying U substitution. But in the beginning, when you were learning about integration in the very first time, you would allow U to be 3x, because this is like an inside function in the chain rule. And by the way, the U substitution, in case you didn't know that, this method is based on, and it's sort of a backward of, the chain rule, okay? Because you have this composition of two functions and so on. All right, so you let du be 3 dx, okay, because du dx is 3, right? And then instead of integrating from 0 to 3, x goes from 0 to 3. Right? X goes from, 0 to 1. But U, because x goes from 0 to 3, 3x goes from 0. What did I say? X goes from 0 to 1. So 3x goes from 0 to 3, right? And then you have E, and of course, this is U. Now, the thing is, I don't have 3 dx in here, right? So what you can do is you can imagine there's a 3, because you really wish there was a 3 here, because 3 dx is what you call du. Well, you can't just pretend like nobody saw you inserting that little 3 in there, right? So in order for you to add that little extra 3 inside here, you have to divide this by 3 on the outside, right? So this will be 1/3 outside here, and you get 1/3, and then e to the u going from 0 to 3, and the answer is 1/3 e to the 3rd minus e to the 0th, which is not 0, which is 1, right? So this is typically what you do. Now, the thing is, we as math instructors encourage you not to go back to x anymore, because this is, once you go into the U substitution, once you do U substitution, there is really no need for you to go back to using x in here. But you could, if you wanted to. And to illustrate this idea of Jacobian and the UV substitution, maybe there is a reason to do so. Okay, so in other words, we said du over dx is 3, right? And so du is 3 dx, okay? But at this point, you can solve this for dx, because that's what you see here. dx is du over 3. Maybe I should write this as 1/3 times du, okay? And so you could go ahead and try to write this in that way. So this is from 0 to 1, and e to the 3x. And instead of dx, what do? Well, dx is, and I'm going to start changing things here. dx is 1/3 du, right? And instead of 3x, of course, that's just u. And then this goes from 0 to 3, right? So in a sense, I know this is exactly what we did before. This is from 0 to 3 of e to the u, and then 1/3 du. Okay, now I want you to look at this. This thing here is a little extra thing that came. Now, here's what happened, okay? And you probably didn't realize this, but there are two universes, parallel universes, okay? One ruled by x and the other ruled by That sounds terrible, huh? The world ruled by X. That doesn't sound right. But anyway, you have this world of X and the world of U. Okay, so it's you against your X, right? So you have this X world, right? In the X world, you had the interval from 0 to 1. Okay, and then you have the U world where the interval now is from 0 to 3. Okay, so what you did is you're trying to solve a problem here, okay, in the world of X. But you realize that it's not so simple, and this one was not so bad. So you decided to go into the world of U, all right, and this is where you started. In other words, you decided you let U, the new variable, to be 3x, which happens to be the inside function of this composition of two functions, right? And then you worked over here in order to solve a problem over here, right? So what you did is you went from this one world of U in the transformation, okay? So the transformation would allow you to go from U to X, right? And that transformation in this case is, what is T of U? Well, let's see. In this case, X, you have to write X as, what is X in this situation? Your X was 1/3 U, right? And so this 1/3 is what appeared here, okay? And so this is dx du in a sense, if you're trying to do that. All right, so this is kind of, backwards of what you had here. Here you define u in terms of x. Here you define x in terms of u. And so that is what we call this transformation. Now, the idea is, you have this inverse transformation that would allow you to go from x to u. And so you're using both of these. Okay. Now, if this is really confusing, don't worry about this. Just remember that there was some sort of a transformation, way to go between the world of x and the world of u. What we are going to do now is to go from the world of xy to the world of uv. Okay, we have this transformation t, but then we have this inverse transformation, t inverse, and then we go back and forth. And then, of course, you will have to put something else in here, all right, which we will be discussing shortly. So just remind yourself that what we are about to do is the two-dimensional version of this U substitution. And when you do so, you always have to add something extra in the integrand, because you're changing from the world of x to the world of u, or you're transforming yourself, or you're moving yourself from the world of xy to the world of uv. Okay, with that notion, let me expand on what I just said here. Okay, so you're trying to solve a problem involving x and y. You have this region R, you're trying to integrate, some function f of xy to. But instead, you identify an appropriate u and v, just like you decided your inside function should be u is equal to 3x. Just like that, you define and identify an appropriate u and v. All right, and this R, which could be complicated looking in the world of xy, could be very simple, maybe like rectangular in the world of uv. That would be the ultimate dream, okay? Because rectangles are much easier to integrate than some weird region R. So you want to go from here to here, but the first thing you do is to identify u and v, and then you define your transformation from the uv world to the xy world, okay? And of course, that has to have the inverse transformation, which will take you from the xy world to the uv world, all right? And so this is what we will be defining. Let me start by saying we want to define, we want t, the transformation from uv to xy. And the way we do this is you have to define what x and y are, right? So x is some function of uv, and y is some function of, no, you can't use the same number, same letter, h of uv. Get that? So in order to go from the UV world to the XY world, you want to define T of UV, where X is expressed as a function of U and V, and Y is expressed as a function of U and V, just like what we did here. Okay, notice here, this is the backward of what we started with, right? Because we started with an inverse transformation here, just like what we're doing here. Okay, so this is the inverse transformation. This is the transformation. Transformation will take you from the world of U back to the world of X, and here from the world of UV to the world of XY. Okay, again, if you are sort of confused about which is T and which is T inverse, don't worry too much about this. What we really need is this. T must be a one-to-one function. Because this is going from R2 to R2, you know, this is a part of R2, and this is also a part of R2. This is called transformation. A transformation is basically a function from a space to itself. So one-to-one transformation is what we need, okay? So that the inverse can exist. You know, if you have not a one-to-one transformation, if two things get to map to one element, then you can't reverse this, you know, these arrows, so you don't have a inverse transformation. So in order for the inverse to be a function, a transformation, you have to have a one-to-one function. All right, and so that is a requirement. Now with this, let me give you a definition of the topic of this section, which is Jacobian. All right, so here's the definition. All right, the Jacobian of TUV, the transformation, is, now remember the setup is this: X is defined as a G of UV and Y is defined as H of UV. The Jacobian is J of UV, and that is the partial of X with respect to U, partial of X with respect to V, the partial of Y with respect to U, the partial of Y with respect to V. And so this is a 2x2 matrix, right? Okay, and so this is, of course, if you want to write this, it's the partial of X with respect to U, partial of Y with respect to V, you go this way, and then minus the product of these, partial of X with respect to V minus times the partial of Y with respect to U. All right, so I'm going to erase this. You know, whenever I write, this is something that you learn, hopefully like in pre-algebra, or I mean the pre-calculus, or it could be linear algebra, but whenever you write a 2x2 matrix and surround that matrix with this, the set of two long lines, this means not just a matrix, but the determinant of the matrix. And that is this times this minus this times this, okay, which is this thing here. All right, so that's the Jacobian. And then, so here's a theorem which will allow you to do this transformation in order to determine the value of a double integral in xy in terms of u and v, right? So if, and again, the same setting, if t of uv is defined, and that's going to be xy, where, okay, and I'll rewrite what I have written here before, because as a part of the theorem, if x is g of uv and y is the h of uv, then the double integral over the region R of f of xy dA, dA is dy dx or dx dy, is equal to, and watch this, okay, it is the double integral over the region S that we called, you know, S is the corresponding part of the region, or the region corresponding to R in the UV plane, not the XY plane. All right, so this is going to be, of course, written in terms of strictly U and V, no more X and no more Y here. G of UV and H of UV, okay, that's what X and Y are, right? And then you take the absolute value of the Jacobian, okay, and then du dv or dv du or something like that. All right, so this is the important part. Let me highlight this. This is the part, I'm going to circle this as blue. This is the part corresponding to this 1/3, remember that was dx du? Okay, instead of this thing here, now we have a full-fledged Jacobian, which is the determinant of a 2 by 2 matrix. In fact, this was really the determinant of this 1 by 1 matrix, which just happens to be the number. Okay, so you have to include this extra thing inside of the double integral, and that part. Okay, this is what dA is. As you do this, and say this is a completely the first time you're seeing this, and this may not make sense. After you see a few examples, and I'll illustrate this with a couple of examples, and then I will actually do something familiar to you. You have already seen one example of this, which you didn't know about, but I will try to show you that. And once you do that, and maybe you can come back to these notes, and I think that would make a lot more sense. All right. And just to add a little extra thing here, in the world of xy, you had this region R over which to integrate the function f. Okay. And what we are doing is trying to solve the same problem in the world of uv, where the region is somewhat nicer, and we call this S. We are integrating not we are integrating f over the region R belonging to the xy plane. But in order to do that, we are going to go into the different world of u and v, where the region corresponding to R is called S, which hopefully is simpler. And we are integrating the function f over here over S. And then the answer is going to be given, right? And that answer is going to be provided to the world of x and y. So this is TUV, okay, where TUV is going to get x and y in terms of u and v. And the way to get there is writing x as g of uv and y of y of uv, okay? And so the transformation here goes this way. The transformation t goes from uv to xy, and the inverse goes from xy to uv. This may be important here. And of course, where the Jacobian is, as I said before, and you can write this in abbreviated term, xu, xv, yu, yv, okay? And so that's what this is. Let me give you an example, and hopefully I will be able to convince you that this is actually a nice thing. Okay, now I have to warn you, this an example, a problem like this will take you a long time, especially when you're not familiar with this. Okay, but bear with me, and then hopefully you will see a significance of this, and then you will have some opportunities to practice this on your homework. All right, so this is an example. Here, okay, I'm going to draw this in a little nicer way, and then ask you a question before we end this portion or this part of the video. Okay, because I wanted this to be precise, I have drawn a rather accurate picture of what we are doing. Okay, so R is this rectangular region. All right, now this, you can tell, this is a pretty hard region to define in terms of x and y, right? I mean, it is a parallelogram, so it is bounded by y is equal to x plus 1, y is equal to x minus 1, so these are parallel to each other with a slope of 1. And then you have equation 3, which is y is 1/3 x plus 3, this is the 3 here. And then number 4, y is 1/3 x plus 5/3, which is also a slope 3. So the line 3 and line 4 are parallel to each other. Line 1 and line 2 are parallel to each other. The equations of all of these 4 lines are listed here, 1, 2, 3, 4 in that order. Okay, what you should notice here is anytime you have parallelograms like this, you can write some relation between x and y in a rather simple way. For instance, equation 1 is, y is x plus 1. You can see that the y-intercept is 1 and the slope is 1. For the second one, the y-intercept would be -1 here if you could extend it. But anyway, you can write this as x minus y is equal to -1. And then here you can rewrite this as x minus y is equal to 1, right? So x minus y actually goes from -1 to 1. Keep that in mind. for 3 and 4, if you multiply both of these equations by 3, you get 3y is x plus 9, which will give you x minus 3y is negative 9. And this one, x minus 3y is negative 5, right? Sure. So both of these can be written in terms of x minus negative 3. And both of these can be written in terms of x minus 1, y, right? So that's the idea. You just kind of observe this. And many times, because it is kind of hard to recognize what u and v should be. By the way, the objective here is to solve this problem. We want to integrate the function x minus y in this over this region R. Okay, so what is that? As it appears right now, R is a difficult region to define in terms of x and y, right? So we are going to do a transformation. You know what the transformation is here? I am going to let u be x minus y, because then you can say u goes from -1 to 1. And then I'm going to let v be x minus 3y, because then I can let v go from -5 to, or -9 to -5, right? So that's a start, okay? So I'm going to rewrite this again. Let u be x minus y. All right, let's call this equation 1, and let v be x minus 3y. That is the equation Roman numeral number 2. Okay, now the reason I set this up this way is because if you remember, I needed to find, to do this, I need to find the equation for x and y. So it's great that I identified u and v this way, but what I really need is to express x in terms of u and v and y in terms of u and v. I haven't done that yet. All right, so in order to find the Jacobian appropriate for this, I need, okay, so this is very much like what we did at the beginning. I decided let u be 3x, but what I really needed was to find x in terms of u, right? See here, you see that x is 1/3 u, and then the derivative of that is equivalent of what we need for Jacobian. So this is what I need to do to find that transformation t, right? So I have defined what u and v are, but in order to calculate this integral, I need to have the Jacobian, which means I need the expression of x and y in terms of u and v. So how do you do that? How do you write x and y in terms of u and v? Exactly, right? You have to solve the system of equations. So I can solve x and y in terms of u and v. So what would be a good thing to do in this situation? I think, see, I see x and y here. So I think I can do equation 1 minus equation 2, right? And see what happens here. Then u minus v is, remember, x minus x is 0. And then negative y minus negative 3y. So what is that? Negative y minus negative 3y. That's negative y plus 2y. So that's 2y, right? So that gives you right away y is equal to 1/2 u minus v, or 1/2 u minus 1/2 v. Get that? All right. So so that's not too bad. All right. So how about how about to find the u? No, y. Okay. So I think what I can do is I can multiply equation 1 by, see, I'm focusing on this thing and this thing again. If I multiply equation 1 by -3, I think that would help. So -3u is equal to -3x plus 3y. Okay, that is the -3 times the equation 1. And then equation 2, I'm just going to rewrite that. V is equal to x minus 3y. You see what happened here? I have 3y and -3y. Now I can add these. All right, so then you get -3u plus v is equal to, and of course this will cancel, but -3x plus x is -2x. And therefore, x is 3/2u minus 1/2v. All right, so I have successfully written x and y in this particular way. So here, TUV is equal to 3/2 u minus 1/2 v, comma, 1/2 u minus 1/2 v. All right. So now we are ready to find the Jacobian. Therefore, the Jacobian is, remember, the Jacobian is XU, XV, YU, YV, and it's a 2 by 2 matrix. And so what is XU? It's a derivative of this with respect to U, that's 3/2. XV is the derivative of this with respect to V, that's -1/2. And then the second row is all about Y. Take this, partial of Y with respect to U is 1/2. The partial of Y with respect to V is -1/2. So you take the 2 by 2 matrix, that's -3/4 minus -1/4, which is -2/4, and that is -1/2. Okay, that is the Jacobian. So maybe I can say I have found the Jacobian. Now, remember, what I had to do was, once I figured what my U and V, I want my U and V to be. I wanted my U to be this, x minus y, and V to be x minus 3y, so that these numbers will be constant. You know, this is, you know, x minus y is a number going from, well, x minus y goes from -1 to 1 and so on. All right, you may need to watch this a couple of times. Once the first time you may watch this and say, yeah, I get a general idea. And the next time you may have to look more carefully at all the details. So anyway, I identified U and V, and I solved the system of equations to find X and Y in terms of U and V so that I can find the Jacobian. Now we are ready to come up with the integral. But let's go ahead and remember this, U and V, right? So I have my equation, the equations, 1, 2, 3, 4. And remember, U goes from -1 to 1, right? So U goes from -1 to 1. That's not 1. And V goes from -9 to -5. Okay, that is what we need to remember, right? Okay. So then I'm going to take the integral. The integral I'm looking for, x minus y dy dx. Okay, remember this was hard to find the limits of and x and y. So instead, now we are going to move from the world of xy to the world of u and v. In the world of u and v, u goes from -1 to 1. V goes from -9 to -5. Okay, now what's x minus y? Well, x minus y, we have a name for this, right? X minus y is exactly what we call u. So we are trying to integrate not x minus y, but in the world of u and v. This is the uv land as opposed to the xy land. In the uv land, this expression x minus y has a simple translation. It's just u, okay? Because that's what you're integrating here, x minus y. You know how it is. Some words in one language is much simpler in another language, okay, if you go to another country. So in the world of xy, this function was called x minus y. In the world of u and v, that same function is translated as u, okay? And then you have, instead of dy dx, remember you have to have the Jacobian or the absolute value of the Jacobian, which is -1/2. The absolute value of that, and then you do dv du. Notice here, this would have been much more difficult because you had to somehow describe that region R, the parallelogram region R, in terms of x and y. And in fact, I don't think that would have been possible. But because I translated that into u and v, these are all constant numbers here, okay? And so that's the power of the UV translation. You will make the region much simpler to describe sometimes if you can find the correct U and V. All right, so let's go ahead and solve this. This is 1/2, and then going from -1 to 1. And basically, you just have U as the integrand. So if you do this integration by V, V goes from -9 to -5. That's only the unit of 4. Right, that's -5 minus -9, that's 4. So the 4 will come in front, and then you just have to integrate u. Of course, this is just 2, so you can write 2 here, and you can just go ahead and integrate u. Okay, so what is the integral of u? Well, that's simple. So this becomes 2u squared over 2 from -1 to 1. Of course, this will cancel. This will be 1 minus, actually 1 square minus -1 square, and that turns out to be 0. Okay, and that's exactly what this is. Now, here's what's just basically in picture. Let me show you what's happening with this. All right, so I will do my best to illustrate what happened here. Region R, remember what that? The region R belonged to the world of X and Y. When you translated that to U and V, right, this is the backward translation or transformation, but you moved that R into the world of U and V, and what happened? The region R was the region S in the UV world where U went from -1 to +1. V also went from -9 to +5, right? And -5. So this was a rectangular region. This is where we were integrating the function, which we used to call x minus y, okay? But in this world, this function was just called u, right? Well, so, and again, the reason this end up with the answer 0 is because u, I mean, this function is symmetric, right? It's an even function. The right-hand side and the left-hand side will be exactly, I'm sorry, it's an odd function. It's exactly the opposite of each other. And so they cancel each other, and therefore the answer turns out to be 0. Of course, it was very hard for you to see that over here. You would have never figured out the answer was 0 over here. Maybe you could have, because x minus y is the one that goes right along here, and one side here, the top side, and the bottom side will negate each other. I don't know. But anyway, that's how you can get the answer here. Once again, let's review the process here. First, you identify u and v so that your bounds will be simple. Try to use u and v, the expressions for u and v, in order to write your x and y in terms of u and v. That's what happened here. Find the Jacobian, insert the Jacobian right at the end of the integrand, between the integrand and the dA part, and then you solve the system, solve the integral, okay? All right, so I think that's, maybe I should summarize this, okay? So let me go ahead and write the summary of what happened here. Maybe I'll use a different color in this case, right? Here's a summary. Okay, so roughly 4 steps. First, define u and v. This is really a hard thing. I gave you u and v in my example, and many times for real, for real life problems, it's hard to find. And so for most of the homework problems, u and v will be given to you. Either that or x and y will be given to you in terms of u and v. In that case, it's fine. It's really easy to find the Jacobian. Okay, some of your homework problems are just that. You'll be given x and y in terms of u and v, and find the Jacobian. That would be a much simpler problem. And then you find the Jacobian, and then you evaluate this as the as you integrate f in terms of u and v, of course, and then you insert, you add, you enter the absolute value of Jacobian here. And then this dA is actually not the same dA as this. This is x and y, right? This is in terms of u and v. But you can have du dv or dv du. Maybe I could put like little prime or something. It's slightly different. Because this dA is referring to the uv world, whereas this dA is referring to the xy world. Okay, so it is, sort of complicated, but hopefully you get the idea. And I'll do another example of this in just a second. Yeah, I'm going to pose this question and let you figure out what the next. Okay. So here's one more example of section 5.7. Find the area of an ellipse. What? Find the area of this ellipse. I don't know if you know the equation for the area of an ellipse. It's very elegant. Okay, but I'll hold on to that just a minute. All right, so this is an ellipse. Okay, And maybe you can figure out, at least you can draw this ellipse and think of what this is in the world of X and Y, okay? So sketch this first, okay? I want you to sketch this, and I want you to figure out what do you think U and V should be, okay? It sounds crazy, but I think you should be able to do this. Try to give yourself maybe 2 or 3 minutes to think about this after you sketch this, and then we'll come back to the next part of this video.